welcome to this lecture from the Smart Buildings and Digital Engineering MSc. I'm Valentina Marincioni and I'm the program lead for this master's program. And today I'm very pleased to be with Dr. Ivan Korolia, who is one of our lecturers as well. So one of my colleagues leading one of the Term 1 module like me. So we are both leading Term 1 modules. And also I'm very pleased to be joined by Pam, who is our student from this year, and Crystal, who is one of our alumni. So we'll hear from them later. But without further, by the way, we are recording, so this session is recorded. And without further ado, I'm going to leave the floor to Ivan. Ivan will talk about one very interesting project we had recently, which is about supermarket decarbonization retrofit, and is actually part of one of the lectures we normally give. So you'll see a bit what we normally discuss in the program, and hopefully it's just going to be an enjoyable lecture for all of us and for me too. So Ivan.
Thank you, Valentina, for introduction. So yes, I'm Ivan Korolia. I'm associate professor in building systems modeling at Institute for Environmental Design and Engineering. I'm a co-founder of this program that we started 8 years ago, was involved in the developing a couple of modules. Now the program is led by Valentina over the last 5 years. And this, let me just move slides. So this presentation is going to have two parts. First part, brief part, is about the program on its own. So a bit on the module structure, same of the program and so on. And after that is going to be a teaser lecture derived from the project I was involved in. So Smart Buildings and Digital Engineering Master Program. The focus of the program, more or less, is on utilization and use of advanced modeling tools, of data analysis, of a machine learning. And what we would like to get from this program, graduates who in the future are going to engineer smarter, more sustainable buildings, which are ultimately also healthier for their occupants. So goal of the program is for students to gain certain level of skills so they can join a new generation of experts to lead the innovation of the engineering, design, and the operation of the integrated building systems for the buildings, current buildings, and buildings that are yet to build and operated in the future. So, among other things, what other students are going to learn within this program is how to utilize different machine learning techniques to improve the building operation, to facilitate the low carbon transition. There is a more or less almost every module a use of Python to apply the different set of advanced analytical methods to support the data-driven decision making in and around the buildings. Different kind of the modeling techniques are presented to students, which can be used to digitalize building systems and optimize the operation of the systems in the buildings. Also, students are learning and applying industry standard tools in the built environment, such as Energy Plus and the Design Builder. And also we expose them to become familiar with certain advanced modeling languages, such as, for example, Modelica and Daimola. So our students are also exposed to industry through a variety of the activities. So there is the engagement with industry through internships, multiple site visits, guest talks. So almost every module would have a guest lecture for someone from the industry, collaborations in the dissertation projects as well, also industry-led awards, and all of this aims to help students to build the skills needed for their career in the digitally driven engineering, design, and consulting. So photo here is from the last year cohort. It was the presentation of the Design Builder UCL Awards for the building simulation modeling. So, and it was think given in the May last year. So one slide on the structure of the program. So it is delivered over the 3 terms in 1 year. Term 1, a couple of modules are dealing with the core necessary knowledge for the whole program. So that is the building physics for sustainable design and performance, led by Valentina. In that module, students are exposed to the core knowledge about the heat transfer in buildings, role of the different materials on the building heating requirements or cooling requirements, so solar radiation, conductive heat transfer, convection, and so on. Second core module is environmental components analytics. That is a module led by me. In that module, we start a bit with thermodynamics so that all students got exposed to the terminology and concepts that we are going to apply in that module and other modules as well. And the focus of that module is on the individual components which are part of the larger systems in the buildings and performance of those components such as heat pumps, boilers, chillers, heat exchangers, their performance under the different operating conditions that they can be faced within the building. Second pair of the core modules is about integrated building design and operation. So in the term 1, integrated building design for health and well-being in a changing climate, that module is more occupant-centric perspective of what occupants are expecting from buildings. So deals with the concepts of thermal comfort, air quality, indoor environment quality, and also surrounding climate. And what are the implications of the climate change on the building performance, and also evaluates the aspect of the passive design measures to improve the performance of the building, so role of the solar thermal control, shading elements, and stuff like that. Second module, term 2 module within this group, is integrated building operation and intelligent controls. In that module, we try to aggregate components which were delivered across a series of other modules into coherent narrative and operation to try to explore how further we can improve operation of the buildings or the design of advanced systems, and what are the role of the control strategies and how that can be applied, and even further develop better operation, sustainability of the buildings, and comfort, indoor air quality for the occupants. A last pair of the core modules deals with advanced methods that we try to pass to our students. Term 1 module is building energy and information modeling. In that module, students learn basics of the modeling in the built environment, so developing a model, creating the model, but through the critical evaluation of the modeling steps. So data, input data, selection of the data, how to analyze the results, how to spot certain maybe mistakes, what are the reasons of model misbehave, errors, and so on. Within part of that module, we also expose certain methodologies, more or less advanced methodologies, which can be utilized in the design process to create better models, such as parametric design, sensitivity analysis, optimization techniques to derive better results from our modeling exercises. Last core module is the term module machine learning in smart buildings. So that is, again, a lot of use of Python and Python libraries with machine learning algorithms. In that particular module, we are trying to use, and we are using the data from real building in operations, and try to analyze that data by applying a different machine learning algorithms and try to see what additional knowledge and understanding of the building in operation we can get just by utilizing those advanced methods across the data that we have access to. So for example, some of the strategies and what we can explore there is fault detection of the system operations just by looking into the operational data from the buildings. On top of that, students also choose from the list of modules, 2 optional modules that they want to attend in the term 2. And in that way, they can expand their knowledge and understanding of various topics around the built environment. Last term is dedicated for the dissertation, so it's a research based project. However, activities for the dissertation starts even in the term 1, and in the early few weeks of the term 2, students already have to think about their research proposal, a research topic, and we engage students to collect the ideas they might want to explore in the term 3 throughout all the modules they attend. So every single topic that they might find interesting, that they would like to specialize a bit more, we advise them to engage with either module lead or other people on the program, so they can find a suitable person or get a suitable person to spend more time working on that topic throughout the summer on the dissertation. So this is more or less what our students are going to get by studying with us over 1 year. So this is first part of this session which I spent speaking about the program. Second part is a teaser lecture from the module I teach on this particular program, and it is about supermarket decarbonization retrofit. So what we try to do as much as possible is to try to link a knowledge that we gain by participating in the research projects and transfer that and utilize that in the lectures that we deliver to our students. So this is literally slides in this teaser lecture. Some of them are slides that were delivered over the last, I think, 2 years, because this project has finished about 2 years ago. So those were slides that were taught in the class in this particular module. So let me start with it. So first, the context for the project. So about supermarkets, so in generally, UK retail food outlets, approximately 3% of all total electrical energy of the UK is consumed by retail food outlets. So those are all kinds of stores. However, these mega stores and large supermarkets dominate that sector. So someone may think 3% is that a lot, that might not be massive. But if we look at the building level and the energy intensity, so per meter square of the area, those kind of properties and buildings are really among the largest energy users per meter square in non-domestic sector when compared to other building types such as offices, schools, and so on. And this is mainly due to massive use of refrigeration. So in those supermarkets, mega stores, we have a lot of fridges and a lot of freezers to store the food. Energy goes for heating, ventilating, and air conditioning those facilities, because users and customers, they have certain expectations about also air quality. Well, they do not want to feel discomfort when they do their shopping. So if space is comfortable, they might be spending more time there. And lighting as well. So lighting, once we go to those kind of supermarkets, we might not observe, but if you look next time, there are not many glazing there. So those are usually boxes with no glazing or very limited glazing. So effectively lighting is switched on all the time. And those kind of large supermarkets are quite often open 24/7. So all this refrigeration, heating, ventilation, air conditioning, lighting is more or less constantly running. So there is a potential for the retrofit of those systems in those kind of stores, and thoughts how to decarbonize, because most of them still use gas-fired boilers to provide the heating. So that was idea behind the research project that we were working on. So project was funded by Innovate UK Knowledge Transfer Partnership. So we teamed with probably the largest company in the UK retail sector. And then from that company, we were able to get a detailed high quality data from several of their mega stores, which we initially started to analyze. So this is the data from 2 of their superstores where we expected, but this just confirmed what we expected, is that refrigeration dominates the electricity consumption, followed by heating, ventilation, and air conditioning system and lighting system. So our approach was, shall we try first to see what we can do about the largest consumers in those particular stores? So refrigeration system and HVAC system. So here is the schematic of what the refrigeration system looks in those kind of stores. So it is based on the CO2 fluid, so carbon dioxide is refrigeration fluid. More or less, it looks like a fridge freezer that we are having in our houses, or like a domestic appliance, just enlarged massively. So in those shops, we have freezers where frozen products, ice creams, frozen fish, and stuff like that are stored. There are a lot of display cabinets for fresh meat, milk, cheese, salami, those kind of the products. Those products, they have to be kept at a certain temperature, -20, -25 for frozen goods, around 5 degrees Celsius in the display cabinets. The major difference comparing to our appliances in homes is that in many stores, display cabinets do not even have doors. And even when they have doors, or these freezers, they are way more frequently open and closed than fridge freezer in our homes. So to be able to keep those products at the desired temperature, we have to start taking the heat from that air, which is way warmer, which gets into those units when doors are open and closed. So that heat, to keep the food at the desired temperature, is extracted and passed to refrigerant or to the fluid which goes through those systems. So there is some heat exchange process. During that heat exchange process, that fluid evaporates. Now in a vapor state, it passes through compressor where its pressure is increased and other parameters as well. So now heat which is taken from the fridges and the freezers is going to be rejected to the outdoor environment through condensers and gas coolers. And after that, through reducing the pressure in the expansion valve, we can make that circle again. Those numbers, 1 to 16 in this chart, are different states of that refrigerant along the process. So this lecture is delivered towards the end of the module, and by that time, our students are already familiar with what the proper thermophysical properties of a matter are, so they would be able to understand and even calculate the states of those properties at these different operating conditions along the process. Let me simplify this further. So just to make the analogy with something which is very popular these days. So if we group these kind of things and present it as a schematic, we can present it as 2 heat exchange processes. In the first one, we take the heat from the source at the low temperature in the evaporator. Fluid which evaporates, going to compressor where we invest some energy in the form of the electricity, increase the pressure, and we reject that heat to the sink at the higher temperature. That is the definition of the heat pump. So this process in the refrigeration system is literally the same process that we have in heat pumps. The difference are the operating conditions and temperatures at which they all operate, but the principles and physics behind is exactly the same. I want you to memorize this because there will be a few more words about heat pumps and how we can utilize already installed equipment for the generating the heat. Second part, second largest consumer is heating system. In those kinds of stores is delivered by air. So there is some air handling unit in which there is a fan to distribute the fresh air throughout the space. That air has to be thermally treated because consumers would not be happy if in the middle of winter, cold outdoor air just drops to back of their neck, so they would feel the discomfort. So that air is treated by using some heating coils, which are connected in those kind of stores to gas-fired boilers, or in the summer using a cooling coil connected to some form of the chiller. What we wanted to explore is, you remember, refrigeration, largest consumer, heat taken from those products and cabinets rejected to the outdoor air. We wanted to explore the opportunity for capturing that rejected heat and try to offset some or all heating requirements provided by gas-fired boiler, and to see whether how much energy we can recover and if there is any need for the secondary heat generator, and what would be the outcome if we apply secondary heat generator by using some electricity-based technology such as additional heat pumps or electrical heaters. So our first step was to analyze the data we received from those stores. So it was annual year of data, high frequency data from perspective that we were looking into. So it was about 45, 50 records per hour. So more or less, we had the minute level data, 1 year of the data about various parameters of the refrigeration system. So what we want to do there is to try to develop the model, first principle model supported with that data, to be able to utilize that model to evaluate other operating conditions for which we did not have data. This is the schematics. On the right-hand side is a thermodynamic chart, pressure enthalpy chart for the particular refrigerant. Our students, by this stage, they know and they have understanding of the meaning of all these lines on the chart and the different states and the different phases of the matter, and what is happening in the chart, energy transfers, and so on. So this is not scary for our students at this stage when this lecture is delivered. In the project, we use Python. We use CoolProp Python module for the thermophysical properties. Our students in this particular module are using the same as a part of their coursework, maybe not at the level of complexity that we utilize for the project, but they are capable of calculating thermophysical properties of a different refrigerants or different matter by using a Python, by using this particular library. Once we develop the model, we want to see how good that model is. 3 stores across the country, high frequency data. We compared results from our model with what is measured and what is given to us in the form of the data. Visual inspection tells us not bad at all. However, something which is not bad for me might be super terrible for you. So what we want to do, and what we had to do there, is to apply some statistical parameters to quantify goodness in quotes of our models. Those kind of statistical parameters is also something that our students are learning and exposed to in several modules, but mostly in machine learning module, because that is the way how we evaluate the quality of models that we are developing. And based on the results that we computed, it's proved that our models are working. R square is one of the measure. 1 is a perfect operation, perfect match. Close to 1 tells us that our model can predict reality very well. If you want to read more about that model development and so on, open access publication in a journal, we published findings from that phase of the research project. Now, once we had a fully working model that we are happy with, quality of the prediction. We wanted to see how far we can go with the heat recovery to replace gas-fired boiler by utilizing already existing refrigeration system which is needed to keep those products at the desired temperatures. To support that, we also had the gas consumption. So this is the annual gas consumption for a heating for one of those stores that we had the data from. And obviously, winter months, a lot of consumption, summer not that much, but never went to zero. UK, summer nights can be a bit coldish. Superstores are operating 24/7. If you go to those kind of stores and pass near those refrigeration fridges and freezers, those cabinets, you can feel that it's not, that it is a bit colder. So there is a need for heating system, no matter that even if it is a summer day in those kind of stores. So there is a gas consumption throughout the year. So what we wanted to see is, okay, the most of energy is needed in the winter time, but those kind of systems for the refrigeration purposes, they are underutilized when it is a cold outside. So keeping food at the minus 25 or 5 degree in the freezers in the summertime requires more refrigeration energy than in the winter time. So to have the reliable system running throughout the whole year, system has to be properly sized. So those kind of, in those particular stores, they have 4 compressors to keep the demand throughout the whole year. So when it is the warmest date, that there is no break in operation and then, stock of the food goes wrong. But that means that in the winter time, most of those compressors are switched off. There is no need for them. And this is a stats where we can see that out of 4 compressors, only 1 is running more than 45% of the time throughout the year. 2 out of 4, 95%. That means that there is a lot of spare capacity in already existing equipment, which we might utilize to harvest the rejected heat. We tested that throughout several strategies, how to capture the waste heat, and these are some of the results. So instantaneous gas saving, depending on the strategy, goes between 50% to completely we were able to replace gas consumption. Overall is a bit lower because instantaneous saving, for example, throughout the summer would record the 1, while there is no that much need for a heating energy. And you can see from the bottom chart that distribution that depending on the strategy, these gas saving ratio varies from like 10-15% up to a 1 for some other strategies. What we observed there that there is a mismatch between recoverable heat and what the heating requirements are. And for some of those strategies, we were rejecting way more heat than what we used to cover the heat requirements, which means that we were producing also a lot of waste, which somehow could be managed and avoided. So particularly in the summer months, that mismatch was quite large. So one of the conclusions is that we would be able to reduce this mismatch, but that would require the operation of those kind of system to be adjusted. So from the almost static control strategies or a rule-based control strategies, we would need to switch to dynamically adjustment of the various parameters of the refrigeration system. And in that way, we would improve overall performance of both refrigeration and heating energy consumption. Results from this second part of the study are again published in another scientific journal. If you are interested about that, you can read. It is also open access. So to conclude this teaser lecture, the learning outcomes for us from this particular project were that we can develop a high quality first principle model of the refrigeration system and validate that model by using the actual data from actual plants. Such model would give us an opportunity to evaluate the performance of the system at different operating conditions and to test the impact of the different improvements. There is opportunity to recover the heat from the refrigeration system. That heat would be wasted otherwise. There is also an opportunity to fully electrify the heating system in certain scenarios without any need for any additional heating energy source, so just by utilizing already existing equipment there. There are certain concerns as well. So that heat recovery system can become also ineffective because of this large mismatch between recoverable heat and heating load. That would require the advanced optimal recovery strategy to be applied. And there might be some consequences as well that if we approach the heating electrification in those kind of the buildings, that would affect the pattern and magnitude of electricity load profiles. So depending on these strategies that we tested, the electricity peak might shift from the midday to early in the morning. They also might shift from the summer months to winter months because we would switch off from the gas to electricity to provide the heating. And there would be differences and maybe increase in average and peak loads. So this is where I'm going to stop with the lecture. If there are some questions about this project or about module or about the program, I'm really happy to answer it. And I'm going to pass back to Valentina to introduce our current and former students who might share their experience on studying with us.
Thank you, Ivan. I have a few questions, but I'll keep it for myself for now. Very interesting presentation, and also a lot of questions for the future sustainability